Our next speaker is Marco Cavallo, who's going to be talking about Clustrophile 2, Guided Visual Clustering Analysis.
Hi Adam, thanks. Hi everyone, I'm Marco Cavallo from IBM Research, and I'm going to present you the work that I did in collaboration with my former colleague Demiralp. So, as most of you probably know, clustering is one of the most widely used techniques for trying to understand structures and patterns in the data during exploratory data analysis. However, as most of you know, this is a very iterative trial and error process that generally requires iterating over a large number of clustering parameters. And by clustering parameters, I loosely define everything that goes as an input to a clustering algorithm. So data samples, data features, the clustering algorithm itself, eventual matrix or affinities, and eventual parameters such as linkage. And one initial issue is how do we explore this vast space of possible solutions, and also trying to choose clustering parameters in not necessarily a blind way. The problem here is that most of the times we don't really have labels, we don't have ground truth. So what we generally try to use is what the so-called internal validation measures that pretty much measure how much clusters are well separated or compact. However, these measures don't tell us much about how the clusters are interpretable or useful to us. So for instance, I can have two very separate clusters, but they can be completely useless for the scope of my analysis. And finally, as always, we have some issues with like high-dimensional data. And in general, for clustering, it is hard to visualize, to visually validate clusters with no bias. So that is why we present Clustrophile 2 as an interactive visual tool to help users and guide them throughout clustering analysis. And we do this at every level of the clustering analysis, meaning the data sample, the clustering result, comparing multiple clustering results, and seeing an overview of the data set. I won't talk much about the support for reproducibility and the scalability of the system, and I will leave it to a separate moment or to later questions. I'm gonna go briefly. I'm gonna go a brief overview of the user interface. So it's a very simple user interface. You see a left and right sidebar for actions such as loading and saving or exporting datasets. And then we have a main view where on the top we have a data table where you can see the raw data and you can perform certain operations such as including or excluding data features in the analysis, or you can ask some statistical information. At the bottom, we can have one or multiple, the so-called clustering views that can be reconfigured in space. Clustering view is the representation of what I call a clustering instance. By clustering instance, I define the output of a clustering algorithm giving a particular set of input clustering parameters. And the idea is to have an atomic representation that allows us to minimally define a clustering results both qualitatively and quantitatively. And for this reason, we chose two types of visualization. One is a scatter plot that fundamentally allows us not to show just the labels, but also the variation within clusters, and a heat map. The heat map is very useful for describing the clusters. Let me explain you quickly how it works. So let's suppose that in this case we have four clusters. The clusters are actually the columns of the data matrix, and the rows are the features. So in this case we have education attainment, student skills, years in education. If I pick, for instance, that cell, in our case red means high values and blue means low values. So in this case I'm considering the features working long hours for the green cluster. I see it's red, so working long hours for that particular cluster is going to be very high with respect to the other clusters. Then if I check a column vertically, I can describe the cluster. So in this case I can say, oh, the green cluster has pretty much blue features everywhere, so those values are going to be very low. Instead they're going to have very high working long hours. If I do it horizontally, I can compare clusters over specific features. So if I'm interested in knowing which are the clusters having the highest index in student skills, I can easily see that is the fourth cluster, whereas the third one, the green one, is actually very low. We also support subclustering, isolation, and naming of both clusters and the clustering view itself. I'm not gonna talk too long about the user interface. I wanna try to focus more like on some contributions, but I'm gonna quickly go through some ideas that we had for providing further guidance. Each clustering view is connected to two panels. The first one is the Help Me Decide panel that, as you may guess, tries to make the user make more informed decisions about the clustering parameters. So we try to use a combination of text, existing literature, and semi-automatic computations and visuals in order to give some insights about the clustering parameters. So in the first case, you can see how we use text, pros and cons, use cases, and links to literature for helping the user choose the clustering algorithm. In certain cases, such as for the metric, we can do some pre-computation and try to possibly suggest a metric to use for the clustering. As far as feature selection, we show before the clustering which are the features that have highest variation. And after the clustering, we show a ranking, for instance, using ANOVA or chi-squared, that tells us which features are considered important for that clustering, so that we can check if we are actually interested in them. We also use, you can see a dendrogram and feature agglomeration. So we fundamentally cluster in feature space so that we can provide the user some ideas on how to aggregate possible features. Below, instead, you see a combination of a generalized elbow plot with silhouette plots to decide a possible number of clusters and eventually how to merge them. The second panel is this a good clustering? That means, is this good mathematically, meaning separation and compactness, but also is it good for my own purposes, so it is useful to me. So the first one is about interpretability, and here we try to use decision trees and decision rules in order to provide a semi-automated description, textual description that is both qualitative and quantitative. We provide another view for validation metrics, and in particular, we can see has certain validation measures are better than other ones depending on the use case, so the user can specify what are his requirements. And the final view in which we show uncertainty, that is, how much is this clustering robust, which data points are likely to change cluster. I'm going to dive quickly to the clustering tour idea. So despite we try to provide insights and suggestions on which parameters to use, the space of possible solution is still too large. So the idea is to try to make the user do big leaps in this hypothetical space and allow the user to have a quick tour of the data, generating solutions that are first very different from each other and possibly with very semantically different meanings. And then when the user provides a feedback and says, oh, I like this idea, I like this type of clustering, then try to optimize in that neighborhood and provide solutions that are more similar and optimized. So in order to do this, we define 3 clustering descriptors. Let's suppose that I have a clustering result A and a clustering result B. B is obtained by changing clustering parameters that generated A. This parameter change, we call it delta P. The delta L is instead the difference in clustering outcome. That is how the 2 clustering results are different from each other. Delta S is instead the score, that is how much clustering solution B is more compact and clusters are more separated with respect to clustering solution A. So the idea is that we start from an initial clustering solution, and then we try to modify slightly clustering parameters in the neighborhood, and we try to understand and estimate how delta L would change with an applied delta P. After this step, we sample solutions in the space, applying hypothetical delta P's, and we select one that is very distant from the current one. The user at any point, in this case, we try to maximize delta L, so generating solutions that are very different from each other. At any point, the user can provide feedback and say, oh, I like it or I don't like it, and then eventually we go back and we open a new branch. When the user likes it, we try, instead of maximizing delta L, we maximize delta S, as to preserve the semantic meaning of the obtained clusters, but to maximize the compactness and separation. To make it more concrete, it looks, this is the actual user interface, and on the left you can see the previous solutions that were generated with this algorithm. In the center you see our typical scatter plot plus heatmap representation with some feedback buttons. An important thing on the right, we can define constraints. So I can say, oh, I don't want the features to change, I want to select them manually, I want the method to remain the same, instead the metric should change, and so on. A very interesting user study we did involves a very researchy and open-oriented task. That is, can you use a data set of symptoms of Parkinson for 8,000 people over 37 dimensions that are pretty much measures of signs and symptoms of Parkinson, and ask and answer the question, can you identify different phenotypes in people with Parkinson's disease? And the interesting part is that this is a complex real-world data set. There is no solution, and we put it as an unconstrained exploration. So the users could take as long as they wanted. And we chose a specific group of 12 data scientists, where we choose 6 with domain expertise on Parkinson, 6 without domain expertise. And we choose them according to 4 categories that are hackers, scripters, and domain and application users that you can find in that paper, Enterprise Data Analysis and Visualization. So the overall workflow of what the data scientists did start with a naive clustering. That is, well, let's start applying a simple clustering and let's see what happens. And they rapidly realized that a naive clustering would not lead to phenotypes. So clusters would be people affected by Parkinson on the left part of the body or right part of the body, or people with low levels of Parkinson, medium levels of Parkinson, and extreme levels of Parkinson. Results that were okay, but not really answering our original question. Then people started to use feature removal and feature selection and agglomeration and started combining features. And the last step that most people did is to try to filter and apply subclustering in order to consider only people. So for instance, let's pick only the people with the clustering on the left part of the body, and let's try to subcluster. Or let's try to consider only the people that took medication or didn't take medication, and let's try to cluster only those. And this is what we call data filtering and isolation. I'm not sure if I have too much time to describe these charts, but we also showed how parameter changes, analysis time, and other parameters of the analysis change based on the user archetype. To go quickly towards insights, so we understood that feature selection is extremely important. It is the parameter that was changed the most, so users would continuously add and remove features to the clustering algorithm. And in particular, we realized that agglomeration is very important, and one feature that was missing and is currently missing in our tool but was very required is feature engineering. We realized that people tend to stick to the algorithms they know. So most of the people that didn't use the clustering tool tried to use k-means and agglomerative hierarchical clustering. And many people realize that this is something you get to trust. So it's not that you try algorithms like this. And despite the Help Me Choose panel provided information about when and how to use certain clustering algorithms, it was not really used. However, we proved that the clustering tool was actually useful to nudge users into thinking outside the box and trying parameter combinations that normally they would have never imagined. Another important point is the ineffectiveness of validation measures. As I said earlier, it's not really useful to know that people with Parkinson are divided into left and right for the purpose of this question. And so validation measures turned out to be useful only at the final step when you want to do smaller refinements, but cannot be used to automate clustering and do ranking. Naming clusters was actually considered very important in terms of interpretability. However, it doesn't scale very well. So I can discuss it later, but we are going towards something that's more like semi-automated summaries. Finally, clustering views turned out to be a good use case for filtering and isolation. Multiple clustering views, we originally thought of them as the user uses different clustering parameters in this view, different clustering parameters in the second view, and they compare. Instead, they mostly use them to apply the same parameters over different data subsets. For instance, I try to apply clustering to the people with Parkinson on the left side and on the right side, and then I match them and I see if the clustering is consistent. So to quickly conclude, clustering is definitely a non-trivial process with lots of iterative experimentation. We cannot fully automate clustering because it has lots of user assumption, prior knowledge, and there's also another thing that we need to fight, that is sticking only to certain parameters or blindly attempt to do certain choices. So our system can try to assist the users in make more informed decisions with the support of statistical analysis that goes beyond the use of just internal validation metrics. Overall, clustering tool demonstrated to be useful for nudge users to think outside the box. And overall, I would say that we urge the development of clustering tools that facilitate explainability, but we also need to keep in mind that the usefulness of a clustering outcome depends on the underlying data, but also on the user task and the context. And that's it. Thanks for listening, and feel free to ask questions.
Please state your name and affiliation.
Davide Canada, TOV. I just want to know if once you have provided the guidance, then you consider in the next loop the user selection for the generation of new suggestions, or if they are static.
You mean in the clustering tool phase?
Yeah, I would say that you rank the parameters, for example, then maybe the user select one. Then do you use that selection for maybe changing the ordering or adding more suggestions?
Okay, the clustering tool, probably we hope to write a separate paper in which we explain it a bit better. But the clustering tool has different components that are, some of them are random generation and some of them are ranking. It means that at certain points of and one of them is feedback. So generally when the user provides feedback, this influences the ranking, but also changes the parameters that get optimized. So for instance, as I said earlier, maybe instead of optimizing delta L, you start optimizing delta S. However, even by doing this, there are certain, certain correlations, certain feature relations that are preserved, sometimes too much. So we add a sort of randomized step in it, so that features sometimes are shuffled, so that features that maybe are too strong. So for instance, in this case, we had the feature that was related to did you take a drug or not before taking the Parkinson assessment. And that feature was like super important in determining the clusters. And some people didn't realize it was in it. So we added a shuffling step that would sometimes remove it so that the users would also be able to see how the clusters would be without that feature. But going back to the question, yes, it's dynamic.
Thanks. First of all, thanks very much. I mean, this is very thorough work, and I think it's very important and it's very well done. So highly appreciate it, really. I'm thinking about something else. I mean, we only should do clustering when there are real clusters in the data. Otherwise, we impose a structure that isn't there. And I wonder if in your very comprehensive framework, whether you also account for that solution, where you say you better regress the model instead of clustering. Do you explicitly account for that option?
Yes, you know, so the tool was born, I mean, I focused it a lot on clustering analysis today, but the tool is in general for exploratory data analysis. So for instance, some people don't even use it much for clustering, and they use it more for like other statistical purposes. I didn't show them, but the interface includes like many other statistical charts and features. Then for this specific use case, we focus on clusters, and sometimes, like in this particular use case, could seem a sort of a let's try to force users in finding clusters. Because for instance, even the interesting thing of the domain expertise. So if you're a domain expert, you say, oh, I'm already searching for this thing. So you're already starting with a mental attitude that says, okay, I definitely need to find this in the data. And some people actually didn't find it. Then, given the question, they were sort of forced to find them. And so, for instance, they tried to select subsets of the data and other subsets, or find the rotations in the data that would actually find the structure. But to your point, we don't actually take it into account specifically in this case, but it's a very important fact that we should consider, I think.
Let's thank Marco one more time.